Okay, so I'll go ahead and get started with this. So this is the review for the practice exam. So we're going to look at, so first thing to note is that, all right, so full disclosure, the practice exam here, first off, we've got like 15 pages. So my practice exam will have like, you'll go up to page 16. Don't worry about that, okay? This has to do with my tendency to put one problem, like to give each problem its own personal page, so you have plenty of workspace to work on. So don't get freaked out about the length. And furthermore, I actually burned some pages on the end I have an entire 4 pages dedicated to extra credit, which not much extra credit, but one of those is like completely blank. One of them is a survey, and then another of then there's actually some extra credit. Also notice that there's 105 points on the exam. That means that basically that there's like a kind of 5-point buffer built in for you. So, let's go ahead and get started. I will put stuff over here, like I'll have a list of like the common list methods and the common string methods in case you forget, like the ones I consider pertinent for their problems. You're allowed to add, so remember these notes over here, they're really important. You're allowed to clarify any answer you give, meaning that you're allowed to basically argue for your answer, and there's been people who've gotten wrong answers correct for making very good arguments. You're allowed to ask for clarification, so you're allowed to ask what the heck I mean. Things are never as complicated as they appear, which is just slow down and think is kind of the advice here. And you never want to leave a question blank, even if you don't know the answer, especially if you don't know the answer. Just try to make a stab in the right direction, because sometimes you might surprise yourself and get like half credit or something. So because we give partial credit, we're big on partial credit. The way my grading scheme works is that if you've got it mostly wrong, like if you got the answer wrong, I look for what I can give you credit for, what partial credit I can give you for. If you got it right, I then look at like, okay, did you make sure that you didn't make syntactical errors or stuff like that? And if you made like some minor mistake, I'll ding you 1 or 2 points on the 10-point problem. Like what I do is I'll treat every single problem like it's its own mini exam. So like 9 points out of 10 is like a 90 on that problem, right? 4 is a 80 on that problem out of 5. Okay, and right, there's 5 points, extra credit points baked in, but we also reserve the right to give you to give extra credit out for really good answers. This might range anywhere between 1 point to 1/100 of a point, so because your answer was actually amusing, but doesn't actually add anything, but it made the grading process more amusing for me, so therefore, yay, 1/100 of a point for you. So first off, you'll get a problem like this on the exam. It's actually going to look exactly the same, except the actual questions are going to be different on the actual exam. So d.previous. So I'm going to go over this one first, and then I'm going to jump around to the harder problems to make sure I get them, because so I'll jump to the end of the exam, and then we'll go and finish the middle. So here, d.previous, right, is C. Previous is B. Next is C. Previous is B, right? So we go back, back, forward, back. So the answer in this case would be B. Does that make sense to everybody? Okay. So the next one, C.next, previous. So that would also be B. All right. And so now let's look at this one. Next, next. Okay. So actually, if we think about it, next and previouses cancel each other out. So there's 2 next, 2 previouses, so they cancel each other out. And a next and previous cancel each other out. Next and previous. So the answer is also B. Those of you who have taken my 1068 class know that on my first exam that I have a bunch of true-false questions, and they're all labeled false for easy grading. That's probably not going to happen there. But if something like that happens, don't freak out. Like, okay, so there's not. Solving one won't give you the other ones, but it's just if you see something, it's like, could he do that? Yes, I am that guy. So I'm going to skip problem 4 over here, but note the problems on the bottom. For all these coding problems under list, you'll have what is the time complexity of this algorithm? I rephrased this on the actual exam to what is the time complexity of what you just wrote. So you want to put that there, what your big O time is. So, but I'm going to skip here because this is probably where, yes. Yeah, it's got to be, so your choice with what you know how to write is either going to be constant time, which is probably not. It's going to, so you're probably going to be writing either a linear time algorithm or a quadratic time algorithm. So it's either ON or ON squared, depending on what you wrote. Yes.
When you like, for example, like this method here, what if you like use like a for loop, like versus like an iterator?
Right.
Do you care or?
Nope, don't care. If you've got an insight like about, well, if it's array list, it's going to be my algorithm's going to be this way. I'm going to assume that the lists that are being used are array lists. So if you figure out, oh, this algorithm, it's going to work differently, then you might want to put that down, and who knows, you might get extra credit. But I'm looking for simple algorithms, and I'm going to treat for analysis, I'm going to treat everything like an array list for those purposes here. Now, let's just look at the linked list stuff first. So first, write a sequence of commands that will remove the tail of a doubly linked list. Okay, 6 points. So let's go ahead and do that. Now, you might be asking why the heck I have you write stuff on the. Let me make sure I'm on the camera. So why in the world am I having you write stuff on paper when it's like this is a programming class? And the answer is because you need to learn how to write code on paper and on the whiteboard, because God knows that like half the interviews out there are on the whiteboard. And also, if you want to express your algorithms and do pseudocode really quickly, which you should be writing pseudocode before you write code, you want to put it on paper first, right? Before you put it on a computer and just start worrying about the syntax. So let's go ahead and write the commands that will remove the tail of a doubly linked list. So we assume that, so we have the tail, right? So how do I remove the tail of the doubly linked list? Well, the first thing I have to do is that I have to do, really this is actually pretty easy. Tail dot, the tail should be equal to tail dot previous, right? So what that's going to do is that if I've got a node over here, right, and for these things you always want to draw them out, right? Here's my tail over here. Tail is equal to tail dot previous, so this is going to move your tail over to here, but it's not going to completely remove that tail, right? Right, it's still attached. Things in Java, things are survive until they don't have anything pointing to them anymore. So I need to make sure that the new tail doesn't have anything pointing after it. So then I go tail dot next is equal to null. That's all I needed for this problem. It's not actually that hard. On the exam, you'll have the inverse of this problem, which is I give you some code, please draw what happened, right? And we will, you're allowed to do that in multiple steps. So let's look at my actual questions here. Write a method that takes in two sorted linked lists of integers and merges them into one sorted linked list and returns them. Since this is a static method outside of linked list, you cannot access the nodes. Honestly, it wouldn't matter. That's just simply this is just simply so that, honestly, you could use it either way. There's a way you can access the nodes, kind of, or go through like a linked list, which is to use Iterator. But this is to get you thinking about, like, maybe I don't need to use a for loop or something. So let's go ahead and think about this. This is like saying that if I want to take if I've got something that looks like this, 1, 3, 5, and as one linked list, right? And I've got 2, 4, 6. I want to merge them together into one list that goes 1, 2, 3, 4, 5, 6, right? I've got two sorted, right? These are both sorted. This is sorted, right? And this is sorted. I want to merge them together and make them one sorted linked list. Now, this is actually part of a problem that we'll learn later in this semester of a recursive sorting algorithm called merge sort. And this is one part of that algorithm, which is merging two sorted lists together into one list. Okay? So how do we solve this? So again, this is a much harder problem. Again, though, I do like the idea of working. My exam does like the idea of working with sorted linked lists. So keep that in mind. But this is one of the harder problems with regards to that. So the idea here is that maybe I could, let's just Now, let's just, ignore maybe differently sized lists right now and just focus on two things being the exact same size. So how do I sort them? Well, I could put them into a, I could, the easy combination solution I would think is 1, 3, 5, right? Move them into one linked list. 2, 4, 2, 4, 6, and then maybe sort it like that, but that's going to take forever, right? Because it's a linked list, right? If I'm going to sort something, that's going to involve going to various indices and moving pointers. That's going to kind of be terrible. Right? So, but that is a solution to put them together into one linked list and then to sort them, but going to be slow. But that is a solution. But we can be a bit clever. It's also going to take like at least O of n squared time, at least, right? And then you have to factor in the amount of time it takes to iterate depending on the sorting algorithm you used. So is there another way to combine them? Well, let's look at my output. I know that I want 1, 2, 3, 4, 5, 6, right? So the idea here is that maybe, well, the 1's going to go before the 2, but the 2's going to go before the 3 because the 2 is less than 3. And the 3 is going to go before the 4, and the 4 is going to go before the 5. We're kind of interweaving them. What if they're not interwoven, though? What if we've got 1, let's go look at an example, change this up a bit. 2, 4, 5, 1, 3, 6, right? So how do I figure this out now? Well, the key to this algorithm is realizing that we can sort these just by looking at the heads of the linked list. Okay? We can just look at the heads of the linked list and then start removing the heads of the linked list. So, right, because we're reducing a new list over here. So, we can do 1 over here. And then we can do, so what we can do is that if we can look at the heads of the linked list. And we can look at which one is smaller. Oh, that's a pretty easy question. Which of these two things is smaller? And not only that, I made them integers so it was easy to compare them too. So I at least gave you that much. So I look at 1 versus 2. 1 is less than 2, I'll put 1 in first. So I'll remove that guy. And now let's just look at the heads of the linked list. Which one is smaller? 2. I'll remove that guy and put him on the new linked list. Which is smaller, 3 or 4? 3 is. Which is smaller, 6 or 4? 4 is smaller. Which is smaller, 5 or 6? 6 or 5? 5 is smaller, so we remove that one. Which is smaller, 6 or well, 6 or anything else. Well, 6 is the only thing left, so we just move it on to the end. So that was actually a pretty useful algorithm. But I don't necessarily want to. Now, mind you, that's going to remove stuff, so I could always make a copy if I needed to. The other thing I can do is I can use an iterator, right? I can create an iterator for A and an iterator for B, just like we did in linked list, and do iter.next to return each every time the big, and to get the first items for each, and then I can use iter.next to update the lists. But let's think about how that works. So the main thing we want to do is, let's see, but let's just assume we want to make this as easy as possible. Don't worry about removing stuff, that we're going to remove stuff from each of these lists. Okay, let's just go ahead and remove them and just create a new list for that. Okay, you might ask me, is that okay? And I'll tell you on the exam, yeah, that's okay. So, because again, this is a new practice problem I came up with, and I needed to be, and I wanted to be, next semester I'll be more explicit with this. So, wow, list A dot size is greater than 0, while there's still stuff in list A, and it's okay if you can't do ampersands, neither can I, so I'll put, so you can use all caps if you need to. Well, list B dot size is greater than 0. While there's still stuff in list A and there's stuff in list B, we want to do this whole comparing the heads of the list thing, right? That makes sense. Let's also create a linked list. I'll just call it out over here, where our output is equal to a new yada yada yada, right? You can write it out on your own. So while there's still stuff in the linked lists, okay, if list A dot get 0 is less than list B dot get 0. So get the head of each. So we're comparing the heads of the two linked lists there. So get 0, that returns the heads. So those are two constant time checks over there. Then out dot add, and actually, so we can do, so we might go like e is equal to list dot get 0, dot get 0, list dot remove. So get the 0th item, remove it, and then out dot add e to, right? Well, technically it's an integer, so I can put that over here, int I, right? But you can actually do that in one line, believe it or not, right? Because remove returns the value that you're removing. So I can just do that as out dot add list A dot remove index 0, which again is a constant time. That's a constant time. Removing is a constant time there. Adding to the end of the list is a constant time. So that's all. Those are just two constant time calls. Okay. Next thing to do. So that was if list A is less than the head of list A is less than the head of list B. So else though, that means list B is smaller. So we do the same thing. Out dot add list B dot remove 0. For the record, I've not actually solved this problem before, or not actually like written code for it. I know how it works, but this is the first time I've actually written this on a board for you guys. So that's also a constant time call. Okay, and that's our loop, right? We just keep doing this same process until one of those lists is empty, and one of those lists is eventually going to be empty because we're removing stuff from them, right?
Are we assuming that there's no equal, like repeating number? Like 0
I mean, if there is though, then if they're equal, then we'll just remove it from B, right?
Okay.
Right? Or you could do it for less than or equal to and do it in list A instead, right? It's an either or. It's this. Did that make sense, right?
Yeah, it's almost catching it in the second part.
Yep. So now though, we might have something like this where we had 1, 2, 3, and 4, 5 over here, and then we had 7, 12 over here, right? So so we might have moved all the items over, and now we have into the list, but list B still has items left over in it, right? Right? We're going to do this algorithm, and either list A or list B is going to have at least one item left over in it, right? Make sense? So we'll just take care of that for both of them. So while list A dot size is greater than 0, I will out dot add remove list A dot remove the head, and then I repeat that for list B. Okay, so I do this so while there's still stuff in list A, I remove it and I remove the head of the list and place it onto the list I'm returning, right? Sorry, place it on the tail of the list I'm returning. Why can I do that? Why can I just simply churn through everything in list that's left over in list A? Well, because if it's left over in list A, all the stuff still in list A is sorted, and we know it's bigger than all the stuff in the output. Okay, so it's either going to be that, and then we just copy this line for list B, because if there's nothing in list A, what will be in list B? And if there's nothing in list B, well, list A will run. Then at the end, remember to return, right? I'm just simply out of white space because my handwriting is terrible. Okay. So that, everybody see how you solve that? Now, what's the runtime of this algorithm? Well, it's actually pretty cool. So what is the time complexity of this? Well, okay. So yeah, it's O of n. Or technically, so O of n is the correct response over here. That would have given you full credit. So assuming that these things are both half of n, right? These are both n over 2 size, or maybe they're just O of n. Each of them are the same size. Right? While for all the stuff in both the lists, I'm going to remove, this is a constant check, this is a constant operation, this is a constant check, this is an operation. So we're going to go through a bunch of items over here. And what's ever left over, this is a constant time check as well. For each item, we're going to check to make sure that there's still an item there, and then remove it, which is in constant time, and add it in constant time. That makes sense? All those operations over here are in constant time, and this algorithm goes over every single item that's input. So it's O of n. More correctly, though, it would be O of n plus m, where n and m, because one list can be like size 10 and the other one can be like size 1 million. Right? But O of n is correct. This just simply means that basically the two things, if they're both the same size, then it's O of n time. Okay, so that was definitely the harder problem, which is why I made it 15 points plus 2 for the other for that. So this one's actually a really nasty problem that I really like. It's actually really nasty. It's actually like kind of an interview problem, and a problem that they would ask you if they're an interviewer would ask you if they're testing you on linked lists. Okay, and the question would be, write a method that reverses a linked list. Okay, and that's a hard one. So we're just going to deal with doubly linked lists for ease of simplicity here. So let's write a method that reverses a doubly linked list. The method will be an instance method for linked lists. So you can use the node, head, and tail references and refer to linked list object using this keyword. So this isn't something that would exist inside of a linked list. All right. So the trickiness of there is just thinking about how I'm going to do this. Now the key here is to draw the appropriate amount of nodes so that we keep track, right? Now, does anybody have a cheap solution, a dumb solution, a ridiculously ridiculous solution? Yes.
Like go around each time, like loop around until the end, and then edit the new link list.
I mean that's a possibility. I'm not sure what you're getting at. What are you?
Like you have to start from the beginning,
okay,
go to the end, and then either remove or add it to another link list, and then do it again over and over.
Gotcha. So basically, keep removing something and adding it. Go through. So basically, create a new linked list, right? And then swap and then say, hey, this is the head and this is the tail, right? So that's actually not too bad, right? Because now with an interview problem, what they'll keep doing is saying, okay, now you don't use any extra space. Now don't do this, right? But right now I'm not putting any restrictions. What you're saying is basically let's create and let's just draw this out before we come up to the solution that we want to code, okay? What you're saying is that in order to reverse this, the way I'm interpreting what you're saying is that I'm going to remove the tail of the linked list and add it to the head of this empty linked list over here. So now this tail becomes the head of this linked list, right? So we create a new linked list in here. We move this one over to here to make this guy the next. Then we move over here and add it to the end of this linked list, right? And we may take this guy and move it to the end of this linked list. That's going to take O of n time. That's a great solution. And and then to copy everything over, you say this dot head is equal to this list's head, and this dot tail is equal to this list, So the idea here, that's actually a really nice and pretty easy solution. So let's write that one. I like this one. I'm thinking of a bunch of other solutions, by the way, but this one's a nice one. So what you're saying is something along the lines of basically while head is not equal to null. So while there's still stuff to move, right? let's go ahead and say, and then we'll create a new linked list, new list over here with that's equal to a new, new linked list, right? Yada yada yada, all that stuff in there. The idea here, right? Assume I added the generics and all that stuff. It's hard to write when I'm stretching up like that or something. Okay, so right. So while the head is not equal to null, what we're going to do is that we are going to this actually is pretty easy. New list dot add tail, right? New list dot add this dot tail, and then this list we are going to remove the size of the list -1, right? Remove the last index, right? So just simply add the current tail, remove the last index, and then we'll keep going, and this dot tail will keep getting updated by removing them. And so this will finally get this to the head, which the head and when we get to the last node, the head and the tail are going to be the same. We're going to remove it and add it to the end of the last list of the last thing in there. Okay. And then, so we've got new list, and now head is null. So now we just say this dot head is equal to new list dot head, and then this dot tail is equal to new list dot tail, right? And that will solve it. That's a problem. Now, so that solves it. What I really like about I like it because it's a very simple algorithm. It's clean. It doesn't take much time. It doesn't take a lot of writing. Doesn't take actually a lot of space on there. It gets you all 10 points because it does what we want. It does what we want. Okay. What would be but if I was an interviewer, which I'm not, but if I was, my objection to this would be, okay, I wouldn't make an objection. I would just simply push you to a more efficient answer, which is saying, okay, but you've had to create a new linked list to do this. Now let's do this without creating a new linked list. Okay? That would be my response to that. Can you do this basically in place, right? And that's a bit of a more tricky challenge. But the idea here is that of thinking maybe just create something else and put them in, that works. The method I was thinking that was very similar to yours was to create a stack and go iterate through the entire linked list and push everything into the stack, right? And then basically, so remove the head, push it into the stack, remove the head, push it into the stack. And then you've got the tail on top, and then keep popping from the stack, and you've got the linked list in order. That makes sense to everybody? Right? Because the first thing in would be the head, and it would be the last thing going out, which would be the new tail. So there's that kind of solution. Do you have a question?
No.
So it would be very interesting to think about how the whole reversing a linked list would work, doing that in place. But that's really tough. Yes.
For the while loop that you wrote down, would you be able to do new list dot add and then in parentheses this dot remove?
Yes, I would be able to do that. I just was, showing that you can do it like this. There's a lot of different ways to write it. All right, so those problems weren't. So this one was pretty nasty. This one though was a lot easier than it looked. Right? It was just right. There's nothing stopping you from using up extra space and copying things over. There's nothing that ever stops you from doing that. Okay? Unless I explicitly tell you can't do that, which I don't think I have. But yes.
For that, if you're setting this dot head equal to new list dot head, wouldn't that make the new list head equal to null?
new lists. No, we're taking this dot head. So we're taking the memory location of the head of the new list and storing it in this dot head. So the head of the list we've already it was the tail of the previous of our original list, right? So we're taking the old tail and making it the head now. So this dot head is null, right? You'd be right if it was new list dot head is equal to this dot head. That would set null. That would set the head of the new list to whole. So null. Yes.
So the old list head just points to the new list.
Yes, the old list head just points to the new list, and the old list tail is now the new list tail, right? Because once we get done with that loop, after we remove everything from it, the head and tail are null, meaning it's an empty list. Oh, there is actually one problem with this, though, which is now the size of our list is 0, right? There is that problem where we've set where the size is 0, right? So we do need to fix that. So we do have to say this dot size is equal to new list dot size. And we can do all this because we're actually inside linked list, right? So that would have docked us a couple points once the professor got clever enough to realize that was an issue. Yes?
So that's basically like making it the pointer so that it's modifying the
this is based
linked list stored. So like we're modifying that linked list.
Right.
But because it's not returning
right.
that linked list, that's what makes it modified in this method.
Yeah. Well, we've already been changed that. Anytime we do a this dot, we're changing it, right? We're inside the linked list, and this is written inside the linked list class, right? That's what I mean by it's an instance method. Yes. This is equal to new list. That would new list. Can I do that? I'm not sure if I can do that, to be honest. I've never actually tried that. I don't know. I'd have to try that and get back to you. Okay, so let me move on to the other to one of the other problems. So this one is actually one that we did in class. This is not a linked list problem, though. I didn't put a section header on there. That's a stack problem, right? We did this. I coded this up in class. A harder version of this. Write a method called bounds paren, which gives you a string with a bunch of expressions, and checks to make sure that the parentheses, only the parentheses, so you don't have to worry about the brackets and curly braces like I did in class, are balanced. It returns true if the expression has balanced parentheses. Right. So everybody remember this from class? So let me go ahead and write it on the board here. So I'm going to assume that that this is balanced by default, right? So I'm going to write return true at the very bottom, just to assume that it's balanced. And as soon as I prove that it isn't, right, balanced, I'll return false. So the first thing I need to do is basically I need to go through everything. So let's create a stack of characters. And this is a string, so it's equal to, it's equal to newest stack of characters. Okay, so for int, so I'll do it the way you would probably do it. Int I is equal to 0, I is less than let's see, what was the turn? It was exp dot length, right? Remember, it's dot length with parentheses for strings, dot size with parentheses for all the collections we're dealing with in class. So for lists I plus plus, because that totally makes sense. Okay. Now we go through this. Car C is equal to expression dot, it's car at car at I. Okay? Right? Make sure that this is being caught. Okay, car at I. Okay. So for every character at I, what are we going to do? Sorry, for every character, what are we going to do? If C is equal to the parentheses character, the open parentheses character, what we found out is that basically we're going to use a stack for this. And we'll just simply push it onto the stack, which we'll call S over here. So S dot push the character onto the stack. So we'll push it onto the stack every time we see one, and we're going to pop from the stack every time we see a closed parentheses. And if we try to pop and there's nothing there, right, then we get an error. And that's how we'll know that we've got or we'll check before we pop it. Basically, what we'll need to do is that we'll push a number of times and we will pop an even number of times. And if we have more pushes than pops or more pops than pushes, then we know that we're not balanced, essentially. Okay? So let's go ahead. And this also makes sure that basically so you can't just count the number of parentheses, right? You have to also make sure that the pushes and pops occur in the same order, right? So you have to be able to push before you can pop. So s.push is equal to C. So now, else if C is equal to the closed parentheses character, what are we going to do? We need to first check if S dot empty, if S dot or is empty depending on which method you use. They both exist. If the stack is empty and we're trying to pop this thing, well, we don't want to pop. So if it's empty and we found a closed paren, well, that means there isn't a matching open paren, which means that it isn't balanced. So we return false. Okay. Else we're just gonna s.pop over here, and we don't have to check if it matches because all we're counting are parentheses. And actually what I can do here now is that when I get to the end, we're going to return s.empty over here. So this will return true if it's empty, but if there's still stuff in it, right? If we push more times than we popped, there's still stuff in it. So we'll return. So in that case, we will return false if there's still more stuff in there. Does that make sense? So this wasn't a particularly hard problem either. We just had to think our way through it and just remember that we saw it. So if you see a stack problem, it's probably going to be something similar to what we've done in class before. Okay. So let's go ahead and go over the analysis, which is the next big portion of this. So a list can be implemented in a number of ways. Compare and contrast an array list and linked lists. In what situations would you use one to implement a list over another? So I'm going to pull up the solution file I had for my previous exam. Okay. So, anyway, so right, the way we wanted to compare, we had array lists and linked lists, and we decided that the way we wanted to compare them, or the way we compared them when we finished learning about array lists and linked lists, was that we compared the add and remove method, right? We compared the get and set method, and we compared how they used up memory, okay? And the add and remove was the really complex one. Get and set wasn't that complicated. So let's go ahead and start with get and set. For an array list, getting an item at a particular index, how much time did that take? It took constant time, right? So let me go ahead. Yeah, so that just took constant time, right, to get something at an array list, right? It took constant time to get something from an array list. For a linked list, if you want to get an item from an array list, how long is that? Oh, sorry, from a linked list, how long is that going to take to get something from a linked list? It's going to take O of n because you've got to seek it, right? You've got to get the proper to the proper location. If you have a if you have a pointer to that item already, that's going to take constant time. But a lot of times you don't. So So array lists are really good at finding stuff just in random orders. Linked lists not so much, but you can iterate through it in O of n, the whole thing in O of n time, in the same amount of time it would take to iterate through an array list. Add and remove though, let's start with the linked list because they're less complicated than array lists. A linked list, right? They're good at adding to the head and the tail. If you are adding or removing to a location you have a reference to, okay? And don't worry about trying to copy this all down. It's going to be on the video, right? So I'm capturing this screen. If the item you're adding or removing a location to, you have a reference to it, like the head or tail, it will take a constant amount of time, right, to add or remove to the head or the tail. Which, by the way, is most of the time where you're going to be adding or removing, right? When we were going through these problems, pretty much everything I added got added to the tail, and pretty much everything I was removing was the head, right? Those were constant time removals for those problems. But if we're trying to remove something in the middle, then first we have to get it, which will take O of n time, and then it will take a constant time to remove that, right? So it will be, but it just say this index, remove it, or this index, add it. It will take O of n time. For an array list, it's not better. It's actually most of the time worse. So in general, it takes O of n time to add something or to remove something from an array list. So given an index to add, if you want to add it to the beginning, you have to shift all the items over. If you want to remove it from the beginning, you have to shift all the items over the other way, right? Same thing with the middle. You'd have to shift half the items over and then the other half the items over. The only exception is adding to the end of the array list, right? Where typically that will take constant time, except when it doesn't, right? Because remember what's the other thing you have to do with array lists? You have to reallocate, right? So you just have to remember that has to reallocate. Now, a lot of times most of the time a reallocation won't happen, but it could, and it can make it much slower, right? And reallocation takes O of n time, and that needs to happen basically once you've added n items to a list, or 10 items to a list, then 20. It doubles each time. So memory usage. How do array lists waste space? How can we, yes?
Because if you reallocate and you only need it for one, you have all the rest of the space.
Right. Exactly right. If you reallocate and then you use only a couple of the bit that you reallocate, maybe like 1% of what you reallocated, 1% of the new space, then you've wasted 99% of the space you just allocated. Okay, what about the memory usage for linked list? What did we say was the waste of memory there? It was possibly, but what was the issue, right? How did that work? Where did we gain those?
What was that?
Where was the extra memory usage coming from?
Each node has to store its item in a memory location or multiple memory locations.
Right, every item, right. It uses up extra overhead, right? Here we're just using an array of memory locations, and so that doesn't use up too much. But in addition to using storing the memory locations of the things we're storing, we also have to store the memory locations of the nodes ahead of us and the nodes behind us, right? So those use up. So we use a bit of extra memory there, right? So that can actually use up. So that adds just maybe, let's say, so it adds overhead. It uses basically twice as much overhead, or 3 times as much overhead, depending on how you want to count it. So that's the issue with there. So let's go back to the problems we didn't do, which were which are actually fairly straightforward to do. Which were these 2 problems over here, the list problem, right? And these are like from lab 2, right? So you can expect actually something that's a bit easier than these. This one's, they'll be about this difficulty. This one's actually harder. So let's go ahead and do this. Suppose you have some list of integers. Write a method that finds the minimum and maximum values stored in the list and returns their sum. And this is just simply testing, can you work with lists, like generic lists, right? Did you actually remember how to do that? Because so the things I look for here to immediately take off a lot of points is people doing something like list, and then they use the array symbol I. No, can't do that. Or that they're here and they use list.next, right? Or they go list.get I and they're panicking and then they go .next, where basically we don't know if these are linked lists, so you can't use them like they're linked and besides, you can't access nodes anyway like that, right? Does that make sense? Make sense what I'm saying? Okay. So here we have to write them as though, so treat them like they're array lists in these. If they're a list, treat them like they're array lists for purposes of writing. So min max plus, let's see, so I do that. Let's see, do I have that hotkeyed? Yes, I do. Okay. So now let's go ahead and solve this one, the min max plus. So here we just need to find the minimum thing and the maximum thing in the list and return their sum, which it already does that returning for me. So that's pretty straightforward. Actually, really easy, just making sure, because we can just simply iterate through this. So for int, we know they're integers, so for int for int x in what do they call it, the list. So for integer x in the list, if x is greater than the min, so actually if it's less than the minimum, then it should be the new minimum. Min equals x. If x is greater than if it's bigger than the biggest number we found so far, max equals x. So problems like this, which honestly that's it, and problems like this is just simply it's a break check basically on anybody who's not who's basically just been plagiarizing their assignments up till now and managed to get through 1068 somehow. I don't know. This one is basically, some questions are designed to differentiate A's and B's and B's and C's. This one's just simply, if I see this one, I'll just yank. If I see something like of this difficulty and it's wrong, I'll just simply yank that exam, go through, and I'll be like, yep, that's a 0. So it won't like kill your entire exam grade. It's just like it's what we call a predictor, right? If you get this question wrong because it's very basic, then it does not bode well for the entire exam. And generally, those exams are very easy to grade because most of the stuff is blank. That's just some insight into the grading pattern. Most people won't get this wrong, or they overthink it or something, because when it's simple, don't overthink it. Really, don't. That's what too many people do. What's the time complexity of this? Well, I just iterated through everything in the list, so it's all that, right? So that was the 2 points attached to that. Remove prefix string. So this one's actually, so that was easy. This one's a hard one. Difficulty's probably somewhere in between this. So why is this one hard? Well, because suppose you have some list of strings and you've got a string prefix. So the first thing is iterating through this list and figuring out, does the string begin with a character? Like begin with the sequence? So that's trivial if you know about the super secret cheat code. But if you don't know about it, then it's slightly less trivial because you have to use substring, but otherwise it's still pretty easy. No, what makes it difficult is that this is an algorithm that is removing things from a list, right? And if you remember from Lab 2, sometimes when you remove stuff from a list and there's two things next to each other that both need to be removed from that list, right? It will yank, they'll shift down and then you skip one of them. Remember that? So, for example, if we're like removing item, so say we've got human hemoglobin hero and humanity, right? This is my input string over here. And say I write an algorithm that basically iterates through this and says, for every item with this, it begins with the prefix, and the prefix I'll be testing is the prefix he. Okay, if it begins with he, I'll just remove it. So human, I don't remove it. I go to hemoglobin, you go to hemoglobin, I remove that, right? I'm at index 1 right now, 2, 3, right? And if I've got a counter, it will be something like this: I is equal to 0, then I go I is equal to 1. Index 1 has hemoglobin, I remove it. So I remove that, but now this becomes index 1 and index 2. So I've removed that, I've done what I said to do. I do I++, I'm at index 2 now, and I skip over hero, right? With, you know, heroes always have that kind of luck not to get killed or anything like that. So we got to be aware of that. So let's go ahead and just, but we'll burn that bridge when we get to it. So first, let's just figure out, let's go through each of the words and figure out, does it begin with that, with the prefix. So for int I is equal to 0, I is less than list, is it list? Yeah, list.size, I wasn't sure if it was words. I++, okay. Okay, so now I've got to figure out how it begins with. So let's assume I don't know the super secret cheat code. How do I check if so string word is equal to list.get I. So the way I can check, does the beginning start with this this prefix? If word dot substring, so the beginning of the word, right, because it's a prefix, right, all the way up to, but not including, prefix dot length, so if the beginning of the word, in these parentheses there, is dot equals, so dot equals prefix, so that's my condition over there. Then what I want to do is that I want list dot remove I, which has that problem skipping stuff over, but I'll get to that bridge when I need to. Okay. First off, this is a bit of an issue here, right? Well, that's not a bit of an issue. That's correct. It's just really long. If only there was like some method, like, I don't know, word dot starts with prefix, which I think there is. It's either starts with or begins with, so there totally is, because that seems like a common enough problem. There's also an ends with. So yeah, if you didn't know about that though, there's substring, and I do give that as a yes.
What if I was like to use dot contains and I didn't think about like starts with, even though like
that would you'd get like 2 or 3 points off, because you got the general idea, you just made a mistake there. It was in terms of like, does it work? Yeah, it's a big mistake there, but it's an exam, so we're lenient there because you got the general idea. Yes.
This starts with take into account capitalization.
I have no clue. I don't care really. Okay, in this kind of problem, I don't care. And if you needed, and if you really had to care about that, convert both of them to lowercase. Right? That would be a thing. Do I care about capital? That's a question to ask me. Do I care about capitalization? So now I have to deal with the double removal problem. Well, there were multiple solutions. The most common one I saw was I minus, right? So if I remove something and it just shrunk, I back up so I can move forward and check the item again. Another common solution was change this if into a while. So basically, you keep checking the same thing, right? You'd pull one off, everything would fall down, and then you check that same index again to make sure that it wasn't something else you had to remove. The other solution that doesn't require any real problems was just change the way that you wrote this and go from the other end. I minus int I is equal to list dot size -1. I is greater than or equal to 0. Right? And that will work without having to make any changes, because whenever you remove something, all the items that are shifting over now are items you've already checked. So you don't have to bother manipulating that to check it. All right, so it looks like it's pretty lively out there. I guess you guys should go join them or something. All right, you've got, so good luck on your exam. I'm going to try to be there for the morning. Honestly, I'll be there for your guys' exam, but I don't know if I'll be there for the morning exam, so we'll see how that goes. Remember, you get one sheet of paper front and back as your notes. And then as far as whether or not you, so when it comes to like a new assignment, I don't know what we'll do this week. If I give you it'll either be something big you get multiple weeks on, or it'll be something smaller than usual.
Would you have like do over spring break?
Oh God, I have to think about spring break now. I'll get into my spring break policy later, but my spring break policy is that I expect you to do as much work as I do over spring break, which is about 0. So I expect basically spring break. I don't account for you to work over spring break. That's essentially it. I expect grad students to work over spring break, but not undergraduates.
Did you get my email about taking the exam?
Yeah, I know it
Stay
is.
sometime.
Here, let me go ahead and quit the recording out.